You think you understand how big space is. You do not. The observable universe stretches 93 billion light years in every direction. A single galaxy inside it holds hundreds of billions of stars, and there are 2 trillion galaxies. Tonight, we travel from your feet on the ground to the absolute edge of everything that exists. We cross black holes, voids bigger than thought, and structures that break the laws of physics as we know them. If you enjoy the journey, subscribe and stay with us. This will change the way you see every single thing. Prepare yourselves. We begin. Stand outside on a clear day and look at the horizon. It feels enormous. The curve of the land stretching miles in every direction, buildings shrinking into dots, mountains fading into haze. Your brain registers all of that and files it under huge. And your brain is wrong. Earth's diameter is about 7,900 miles from one side to the other. That sounds massive. But here's the thing your mind quietly skips over. If you drove a car at 60 miles per hour, never stopping, straight through the planet, it would take you about 5.5 days to come out the other side. 5 days. You have probably spent longer on a road trip through a few states. Now picture a basketball. Smooth, round, about 9 inches across. If Earth were shrunk down to that basketball, Mount Everest would be a bump you could barely feel with your fingernail. The Mariana Trench, the deepest point on the planet, 7 miles straight down, would be a scratch thinner than a sheet of paper. Every ocean, every mountain range, every city ever built by human hands, compressed into something you could hold in one palm. That should already feel strange, but stay with it, because it gets stranger. Earth's surface area covers about 197 million square miles. To walk every inch of dry land on this planet without rest would take you over 22 million hours. That is longer than recorded human civilization has existed. You could walk your entire life, every waking hour, and still cover only a fraction of the ground beneath your feet right now. Here is the detail that tends to stop people cold. If you unrolled Earth's surface into a flat sheet, it would cover roughly 700 million square miles. The entire United States, with every road, every city, every national park, covers about 3.5 million square miles. The United States fits into Earth's total surface about 200 times over. And you thought you knew how big your own country was. Your brain builds its sense of scale from experience. You have walked a mile. You have driven 100 miles. Those distances feel real because your body has moved through them. But no human being has ever experienced Earth as a whole object. Astronauts who have seen it from orbit describe a sensation that has its own name, the overview effect. A sudden, gut-level understanding that the planet is one thing, fragile and finite, wrapped in a paper-thin layer of air. Many of them report crying. Several describe it as the most disorienting experience of their lives. And these are people trained to stay calm under extreme pressure. The atmosphere, that blanket of air keeping every living thing alive, extends about 60 miles above the surface. 60 miles. If Earth were that basketball again, the atmosphere would be thinner than a coat of paint. Every breath you have ever taken happened inside that invisible coat of paint, clinging to a spinning rock. And yet, for most of human history, this rock felt infinite. Explorers spent lifetimes crossing oceans and never reached the other side. Entire civilizations lived and died without knowing other continents existed. The planet felt endless because our legs and boats moved slowly enough that it could trick us. Science pulled back the curtain. The planet is finite, measurable, and almost shockingly small once you understand what is waiting beyond it. Because the next step outward is not just bigger, it is a different category of size entirely. And it starts with something you have looked at your whole life without truly seeing it. The moon. Look up on a clear night and the moon seems close. Close enough to feel personal. Close enough that people wrote poems about reaching it for thousands of years. The truth is, the moon sits on average 239,000 miles away from Earth. That number needs a human frame to land properly. If you lined up every country on Earth end to end, all 195 of them, their combined length would fall short of the distance to the moon. Every road ever paved, every border ever drawn, every landmass humans have ever walked across, stacked in a line, and the moon sits beyond all of it. During the Apollo missions, astronauts traveled that distance in about 3 days. 3 days of floating in a metal capsule smaller than a studio apartment, with the blackness of space pressing against every window. When they looked back at Earth, it had already shrunk to the size of a marble. 3 days of travel, and home was a marble. Here is something confirmed by science that almost nobody pictures correctly. You could fit all 7 of the other planets in our solar system: Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune side by side in the gap between Earth and the moon. All of them, with room to spare. The space between us and the moon is so wide, it swallows entire worlds and still has breathing room. The moon's gravity controls Earth's ocean tides. Every high tide and low tide you have ever seen at a beach is the moon pulling at the water from 239,000 miles away. That gravitational reach across that distance is rearranging oceans every single day, and the moon is drifting. Scientists have confirmed this. Every year, the moon moves about 1.5 inches farther from Earth. 1.5 inches sounds like nothing, but over millions of years, it adds up. Billions of years ago, the moon was dramatically closer. It appeared 3 times larger in the sky. The tides it created were colossal. Some researchers believe they may have played a direct role in stirring the chemistry that eventually led to life on Earth. The moon has been slowly saying goodbye for billions of years, and we are only now measuring it. Laser beams bounced off reflectors left on the lunar surface by Apollo astronauts allow scientists to track this drift with extraordinary precision. This is confirmed. The moon is leaving, 1.5 inches at a time. There is a number tied to the moon that tends to produce silence. The surface of the moon covers about 14.5 million square miles. That is roughly 4 times the size of the United States. A world-sized object hanging in your sky every night, and most people have never truly computed its size against something they know. Standing on the moon, the sky is always black. No atmosphere means no scattered light, no blue sky, no sunrise colors. Earth hangs overhead, 16 times larger in the sky than the moon appears from Earth, hanging perfectly still because the moon always shows us the same face. The far side of the moon spent all of human history unseen. We only photographed it for the first time in 1959. And now comes the step that breaks the first real mental barrier. The moon feels far. 239,000 miles of empty space feels like a genuine abyss. But that gap, that staggering distance your mind just barely accepted, is a rounding error compared to what sits at the center of our solar system. The sun is waiting, and its scale belongs to a different universe entirely. Picture the Earth. Hold it in your mind. That basketball-sized marble with its paper-thin atmosphere. Now picture 1,300,000 of them crammed together inside a single sphere. That is how much space the sun occupies. 1,300,000 Earths, packed inside one star. The sun's diameter stretches 865,000 miles across. If you drove your car at 60 miles per hour along the sun's equator without stopping, the trip would take over a year and a half, just to go around the outside once. Stand at the surface of the sun, and the heat does not just burn you, it converts you into plasma before you even arrive. The surface temperature sits at around 10,000 degrees Fahrenheit. The corona, the outer atmosphere, somehow reaches millions of degrees, a mystery that science has confirmed but still cannot fully explain. Scientists have a theory involving magnetic wave energy, but the precise mechanism remains under active investigation. Now, picture the sun from Earth's distance. 93 million miles away, it still appears large enough in the sky to blind you in seconds if you stare directly at it. That is 93 million miles of empty space between you and an object whose light reaches your skin in 8 minutes. 8 minutes of travel at the fastest speed anything in the universe can move. Here is the scale comparison that tends to produce stunned silence. If the sun were hollow and you placed Earth inside it at the center, the moon's entire orbit around Earth would fit inside the sun with space left over. The moon traveling its full circular path, 239,000 miles from Earth, drawing its complete loop, the entire ring of that orbit sits comfortably inside the sun. That is how large the sun is relative to the Earth-Moon system you just spent a chapter processing. The sun accounts for over 99% of all the mass in the entire solar system. Jupiter, the largest planet, a world so big 1,300 Earths could fit inside it, represents most of what is left. Everything else, Mars, Earth, Saturn, Uranus, Neptune, every asteroid, every comet, every moon of every planet, all of it together makes up a fraction of the solar system's total mass. Every second, the sun converts about 4 million tons of its own mass into energy through nuclear fusion. 4 million tons per second, gone, transformed into the light and heat, streaming outward in every direction. The sun has been doing this for about 4.5 billion years. It has enough hydrogen fuel remaining for roughly another 5 billion years. By cosmic standards, it is middle-aged. And here is the detail that opens the next door. With all that size, all that mass, all that power, the sun is classified as a yellow dwarf, an average star, a medium. In the neighborhood of the galaxy, the sun is unremarkable. There are red dwarf stars, smaller and cooler. There are blue giant stars that make the sun look like a pebble beside a boulder. The largest known stars in the Milky Way are over 1,000 times wider than the sun. If one of them replaced the sun at the center of our solar system, its surface would extend past the orbit of Jupiter. Something that enormous is out there, inside our own galaxy. And the galaxy itself is something your mind has not been asked to picture yet. What waits ahead is the kind of scale that stops feeling like astronomy and starts feeling like something else entirely. Right now, light is leaving the sun and traveling toward you. It crosses 93 million miles of empty space. It arrives at your skin in 8 minutes. You feel it as warmth. You do not think about where it came from or how long it traveled to reach you. But those 8 minutes carry a hidden weight that most people never sit with. If the sun disappeared at this exact moment, you would have no idea for 8 minutes. The sky would look exactly as it does right now. The warmth on your skin would continue. Birds would keep singing. Traffic would keep moving. 8 full minutes of a normal day, while the center of the solar system no longer existed. Then the light would stop. This is confirmed physics. Light travels at about 186,000 miles per second. At that speed, the journey from the sun to Earth takes just over 8 minutes. That gap between event and awareness is real. When you look at the sun, you are seeing it as it was 8 minutes ago. You are looking into the past every time you glance at the sky. This delay has a name, light travel time, and it scales with distance in a way that starts small and grows terrifying. The moon's light reaches you in about 1.25 seconds. So the moon you see is 1.25 seconds old. The sun is 8 minutes old. Mars, at its closest to Earth, shows you an image that is about 3 minutes old. At its farthest, that delay stretches to over 20 minutes. Jupiter's light takes between 33 and 53 minutes to arrive, depending on where both planets sit in their orbits. So when scientists sent commands to spacecraft orbiting Jupiter, they waited nearly an hour just to know if the spacecraft received the message. Another hour for any response to arrive back. Pluto sits so far out that light from the sun takes over 5 hours to reach it. The sun, from Pluto's surface, looks like a bright star. Extraordinarily bright compared to any other star, but a star. The warmth that heats every ocean on Earth that powers every weather system, that keeps every living thing alive, arrives at Pluto as a faint point of light, and a temperature hovering near negative 370 degrees Fahrenheit. Now, apply this same logic backward. When you look at the night sky, every star you see is an image from the past. The closest star beyond our sun sends light that takes about 4 years to reach us. So that star, as you see it tonight, is 4 years old. Some of the stars visible to the naked eye are hundreds of light years away. The light entering your eye right now left those stars before your grandparents were born. Some stars visible in the sky no longer exist. They exploded centuries ago, and the news has not arrived yet. This is confirmed. Astronomers observe it constantly. Stars vanish, and the universe does not immediately tell us. 8 minutes is the smallest version of this delay in our daily lives. 8 minutes between reality and our experience of it. Between fact and knowledge. Between the universe as it is and the universe as we see it. And if those 8 minutes represent the margin between life and extinction, the distances ahead represent something far harder to hold in the mind. The edge of our solar system is so far that the speed of light takes years to reach it. And what sits at that edge is something most people do not even know exists. In 1977, humanity launched 2 spacecraft called Voyager 1 and Voyager 2. They left Earth aboard rockets, swung around planets to gain speed, and headed outward. Over the following decades, they became the most distant human-made objects ever to exist. Voyager 1 is currently the farthest, sitting over 14 billion miles from the Sun. 14 billion miles sounds unreachable, and relative to everyday life, it is. 14 billion miles is a distance that collapses all human transportation into meaninglessness. Voyager 1 travels at about 35,000 miles per hour. That is fast enough to cross the entire United States in about 5 minutes. Fast enough to circle Earth in under an hour. At that speed, the spacecraft has been flying for nearly 50 years and covered 14 billion miles. Now here is the measurement that changes the picture entirely. The solar system does not end at 14 billion miles. Scientists define the boundary of the sun's influence, where the sun's outward stream of particles finally gives way to the space between stars, at roughly 11 billion miles from the sun. Voyager 1 crossed that threshold in 2012. It is now in interstellar space, the region between star systems. But the solar system's gravitational reach extends far beyond that boundary. The full gravitational domain of the sun stretches to a region called the Oort cloud. The inner edge of the Oort cloud sits roughly 2,000 times farther from the sun than Earth does. The outer edge sits perhaps 100,000 times farther. At that distance, the sun looks like just another star. Dim. Unremarkable. At Voyager 1's speed, reaching the inner edge of the Oort cloud would take about 300 years. Reaching the outer edge would take about 30,000 years. Crossing all the way through and emerging on the other side would take roughly 70,000 years. 70,000 years. Modern human civilization is about 12,000 years old. The pyramids of Egypt are roughly 4,500 years old. We have been using written language for about 5,000 years. 70,000 years ago, humans were still sharing the planet with other human species. And Voyager 1, the fastest object humanity has ever sent into space, would still be inside our own solar system. This comparison does not mean the spacecraft is slow. It means the solar system is incomprehensible. Even at speeds no human body could survive, even at velocities that shatter every earthly intuition, the structure we live inside stretches so far that generations would be born, live full lives, and die before the journey ended. Scientists have identified thousands of comets that originate from the Oort cloud. When gravitational disturbances send them falling inward toward the sun, their journey takes millions of years. Some of the comets we observe in our night sky have been traveling toward us since before dinosaurs walked the Earth. They are visitors from the outermost rim of home. Every so often, a comet arrives that takes over 1 million years to complete one orbit. It swings around the sun and heads back out to the dark where it came from. The next time it returns, our sun may have already changed beyond recognition. And this Oort cloud, this frozen outer shell of our solar system, sits inside a galaxy so vast it makes the solar system feel like a single grain of sand on a beach that stretches to the horizon. The nearest star to us is waiting just outside, and the number of years it would take to reach it will make 70,000 feel small. Before we step outside the solar system entirely, there is something out in the dark that most people have never heard of. A structure so distant and so enormous, it wraps around everything we have ever sent into space, everything the sun's gravity touches, everything that belongs to home, the Oort cloud. Scientists have never directly observed it. No telescope has imaged it. No spacecraft has reached it. Its existence is inferred from the behavior of long-period comets. Comets that swing around the sun on orbital paths so enormous, they take millions of years to complete one loop. When scientists trace those paths backward, they all point to the same vast region of space surrounding the solar system at enormous distance. This is a confirmed scientific theory, strongly supported by evidence, though direct observation remains beyond our current capability. The Oort cloud is thought to contain trillions of icy objects, frozen remnants from the formation of the solar system over 4.5 billion years ago. Each one a frozen relic, a time capsule from the birth of everything familiar to us. They sit out there in near total darkness, at temperatures approaching the coldest possible, barely moving, held in the sun's gravitational grip by the thinnest thread. Picture the solar system as a city. The sun is the city center. Earth is a neighborhood about 5 miles from downtown. The outer planets stretch out to maybe 20 miles. Voyager 1, the farthest human-made object, sits at about 100 miles from the center. The inner edge of the Oort cloud begins at roughly 2,000 miles from that same downtown. The outer edge reaches out to perhaps 100,000 miles. The city metaphor breaks down because no city ever built even approached those proportions. The Oort cloud does not just surround the solar system, it engulfs it. The planets, the asteroids, the entire disk of orbital motion we think of as the solar system, all of it sits nested inside the Oort cloud like a seed inside a beach ball. And the ball is mostly empty. Trillions of objects spread across a sphere of space so large that each object is typically separated from its nearest neighbor by millions of miles. Out there, alone in the dark, with the sun reduced to just another faint star, each icy rock drifts in silence. Something occasionally disturbs them. A passing star's gravity, a subtle gravitational ripple from a distant object, a nudge too small to name. That nudge sends a comet falling inward toward the sun, beginning a journey that takes millions of years to complete. When it finally arrives in the inner solar system, it grows a tail. We call it a spectacular celestial event. Prehistoric humans watched the same comets and had no framework for what they were looking at. Here is the scale detail that tends to produce quiet. If you shrank the entire solar system, the sun and all its planets and moons, down to the size of a quarter, the Oort cloud would extend in every direction to about the size of a football field around that quarter. Everything we have explored, every mission, every signal, every photograph, the quarter at the center of a football field. The nearest star sits just beyond the outer edge of our Oort cloud, just beyond home, and the distance between home and that star is something the fastest machine we ever built cannot cover in a human lifetime, or 10 human lifetimes, or 1,000. The nearest star to our sun is called Proxima Centauri. It sits about 4.25 light years from Earth. 4.25 years of light travel. Light moves at 186,000 miles per second. It crosses the continental United States in about 1/100th of a second. In 4.25 years, that speed carries light across approximately 25 trillion miles. 25 trillion miles. Your brain will try to file that number somewhere familiar. It cannot. There is no familiar shelf for 25 trillion miles. So here is a version that might land differently. If you walked at an average human pace, about 3 miles per hour, without ever stopping, no sleep, no food, just continuous forward motion, it would take you roughly 2 billion years to reach Proxima Centauri. 2 billion years of walking. The Earth itself is only 4.5 billion years old. You would arrive having spent nearly half the planet's entire existence in motion. Voyager 1, traveling at 35,000 miles per hour, would take about 70,000 years to cross the same distance. And Voyager 1 is not headed toward Proxima Centauri. At its current path and speed, it would take about 73,000 years to reach the star it happens to be aimed at, which is a different star entirely. Here is the confirmed fact that tends to produce a specific kind of silence. Proxima Centauri is the closest star. The second closest is slightly farther. The third closest is farther still. The galaxy contains between 200 billion and 400 billion stars. Most of them are separated from their neighbors by distances similar to or larger than the gap between our Sun and Proxima Centauri. The galaxy is almost entirely empty space between stars. Proxima Centauri has a planet. Scientists confirmed this, a rocky world sitting in the zone where liquid water could theoretically exist on its surface. Scientists call it Proxima b. If life exists there, it sits 4.25 light years from us. If that civilization sent us a radio signal today, we would receive it 4.25 years from now. If we responded immediately, their scientists would wait another 4.25 years for our reply. A single exchange of messages would take almost 9 years. Any conversation between civilizations at this distance would span generations. Question sent. 9 years pass. Answer received. Another 9 years for the follow-up. Science fiction imagines faster-than-light communication as a solved problem. Physics, as currently understood and confirmed, says it is not possible. So two civilizations separated by the shortest gap between neighboring stars cannot have a real-time conversation. They can only exchange slow letters across the dark, each one taking years to arrive. And Proxima Centauri is our neighbor, our immediate neighbor, one step from home. The Milky Way stretches 100,000 light years from one end to the other. The distance to Proxima Centauri, the closest star, is 4.25 light years. To cross our own galaxy at that same speed, Voyager 1's speed, would take over 1.5 billion years. The galaxy holds hundreds of billions of stars, and we have not meaningfully explored the space between even two of them. What the full galaxy looks like from the outside, its true shape and size, is something even our best telescopes can only partially reveal. And what lives at the center of it should not be there. Stand on a beach and pick up a handful of sand. Squeeze it. Feel the grains between your fingers. A single handful of beach sand holds roughly 10,000 grains. A square meter of beach, just a small patch at your feet, holds several million grains. All the beaches on Earth, every coastline, every dune, every sandy shore, holds an estimated 7.5 quintillion grains of sand. The Milky Way holds somewhere between 200 billion and 400 billion stars. That is a confirmed scientific estimate. Each star its own sun, many larger than ours, some smaller, scattered across a disk 100,000 light years wide. If that number still feels abstract, try this comparison. If every star in the Milky Way were a grain of sand and you poured them out, you would need a beach roughly 10 times larger than every beach currently on Earth, combined just to hold them all. Now add the planets. Scientists estimate there are more planets in the Milky Way than there are stars. Some stars have 1 planet. Some have 6, 7, 8. Our Sun has 8. Many stars we have studied harbor planets in zones where liquid water could exist. The total number of planets in the Milky Way sits in the trillions. Confirmed. And yet, the vast majority of the galaxy has never been observed up close. Our telescopes have identified and catalogued roughly a few thousand nearby stars in detail. A few thousand out of 2 to 400 billion. That is like studying 3 or 4 grains of sand from that entire global beach and claiming to understand the beach. Here is the structural detail that tends to stop people. The Milky Way is a spiral galaxy. It has a dense central bulge surrounded by a disk of arms curving outward like a pinwheel. Our solar system sits on one of those arms, about halfway between the center and the outer edge. We do not live in a particularly special location. We are in the suburbs of the galaxy, far from the crowded, energetic center, far from the quiet outermost fringes. A quiet, unremarkable address. From directly above or below, the Milky Way would look like a glowing spiral disk, beautiful and vast. We have never seen it from that angle. We live inside it looking outward, which is why the Milky Way appears as a faint band of light stretched across the night sky. We are inside the photograph, trying to understand the image from within. The galaxy is also rotating. The solar system orbits the galactic center once every 225 to 250 million years. This is confirmed. One full orbit is sometimes called a cosmic year. In all of recorded human history, in all 5,000 years of writing and civilization, Earth has moved less than 1/10,000th of the way around the galaxy. We have existed for a heartbeat of one rotation. The galaxy's gravity holds all of this together. Stars and planets and gas clouds and dark matter, all orbiting, all in motion, a system too large for any single mind to hold. And at the center of this pinwheel of hundreds of billions of stars sits something that should not be possible. A single point in space that contains 4 million times the mass of our entire sun, compressed into an area smaller than our solar system. It is awake, and it is waiting. If the Milky Way were a city, our solar system would be a house in a quiet neighborhood, about halfway between downtown and the outer ring road. Close enough to feel the influence of the city center, far enough to avoid the chaos happening there. The Milky Way spans 100,000 light years from one edge of the spiral disk to the other. Light, the fastest thing that exists, would take 100,000 years to cross it. A commercial airplane flying at 500 miles per hour would need over 125 billion years. The universe itself is only about 13.8 billion years old. The plane would need to fly for 9 times the current age of the universe to cross our own galaxy. The disk is not just wide, it has structure. Scientists have confirmed the Milky Way has at least 4 major spiral arms curling outward from the central bulge, like a slow, eternal pinwheel. Our solar system sits in a smaller arm called the Orion arm, or sometimes the local arm. It is a secondary feature of the galaxy, branching off from one of the major arms. We are not even on a main road. We are on a side street. The central bulge of the Milky Way is dense with old stars, many billions of years older than our sun. The stars there are packed so closely together that from a planet in the bulge, the night sky would blaze with thousands of stars bright enough to cast shadows. No true darkness, no quiet night, just permanent stellar firelight from every direction. Out here in the suburbs where we live, stars are more spread out. The night sky shows us several thousand stars visible to the naked eye, but that is a tiny local sample. The vast majority of the galaxy's hundreds of billions of stars are too far away to see individually. They blend together into the soft glow of the Milky Way band across the sky. A highway of combined starlight from billions of suns too distant to resolve. Here is the detail that rearranges the mind. The light we see when we look at the Milky Way band in the sky left those stars anywhere from a few hundred to tens of thousands of years ago. Some of that light predates human civilization by thousands of years. Some of it left its source before our ancestors discovered agriculture. The galaxy is also warped. Scientists confirmed in 2019, using precise measurements of star positions, that the Milky Way's disk curves upward on one side and downward on the other. A slow, enormous warp. The exact cause is still under investigation, possibly from past interactions with other galaxies, but the warp itself is confirmed and measured. We also cannot see the center of the galaxy with visible light. Too much gas and dust blocks the view. Astronomers use infrared and radio telescopes to pierce through and observe what sits at the galactic core. What they found changed our understanding of what galaxies are built around. Something anchors the center of nearly every large galaxy in the observable universe. A thing that swallows stars whole, bends space itself, and at the center of our own Milky Way has been directly imaged, confirmed, and measured. 4 million solar masses compressed into a space our solar system could fit around. It is time to look directly at the thing that lives at the center of home. In 2022, astronomers released an image that stopped conversations around the world. A glowing orange ring of light surrounding a dark circle, blurry but unmistakable. The first direct image ever captured of the supermassive black hole at the center of our galaxy. Scientists named it Sagittarius A star. This object is 4 million times more massive than our Sun. If you could put it on a scale, it would outweigh 4 million suns. Every single star in our Sun's weight class, multiplied by 4 million, compressed into a single point in space. The region of no return around it, the boundary called the event horizon, stretches roughly 15 million miles across. That is larger than the distance from Earth to the Sun. You could fit the entire Earth-Sun gap inside the boundary of this black hole's point of no return. Cross that line, and the laws of physics, as we understand them, stop protecting you. Confirmed by general relativity, confirmed by observation. Here is the detail that reframes the scale. Sagittarius A star sits about 26,000 light-years from Earth. 26,000 light-years, and yet its gravitational influence shapes the behavior of stars throughout the galactic core. Stars near the center have been tracked for decades by astronomers. Their orbital paths curve sharply and rapidly around a central point where nothing visible sits. Only the black hole. Those orbital measurements gave us the black hole's mass long before we had an image of it. Watching stars bend their paths around an invisible anchor, calculating the force required to produce those curves, scientists pinned down 4 million solar masses with extraordinary precision. This is confirmed by decades of observational data. Sagittarius A star is quiet by supermassive black hole standards. Some black holes at the centers of other galaxies are actively consuming enormous amounts of material and blasting jets of energy millions of light years into space. Those are called active galactic nuclei, and they can outshine their entire host galaxy. Our black hole is comparatively calm, consuming relatively little, not currently producing devastating jets. That is a fortunate reality for Earth. A truly active version of Sagittarius A star would likely sterilize the inner galaxy. Scientists believe Sagittarius A star formed over billions of years, growing by consuming gas, dust, and stars that wandered too close. Every large galaxy in the observable universe appears to harbor a supermassive black hole at its center. This is a confirmed pattern. The relationship between a galaxy's mass and its central black hole's mass follows a consistent ratio, suggesting the two grow together, each influencing the other over billions of years. The image released in 2022 required astronomers at 8 different radio telescopes around the world to synchronize their observations, effectively turning Earth itself into a single enormous telescope. Even then, the resulting image required 2 years of data processing. The object they photographed sat 26,000 light-years away, and the ring of light visible in the image is the glow of superheated gas orbiting just outside the point of no return. Now, pull back from that image. Hold the black hole in mind. Then remember it sits at the center of a galaxy 100,000 light-years across, and that galaxy, with its 400 billion stars and its ancient black hole core, is one of dozens of galaxies being pulled together by mutual gravity in our immediate cosmic neighborhood. And among those dozens of galaxies, one is heading directly toward us, on a collision course, and it arrives in about 4 billion years. The center of the galaxy is a place where physics operates at extremes we can barely describe. Near the core, Gravity from the supermassive black hole, Sagittarius A star, reaches out and accelerates everything around it. Stars that orbit near the center do not behave like anything in our quiet suburban neighborhood of the galaxy. A star designated S2 by astronomers orbits Sagittarius A star on a path that brings it closer to the black hole than any other observed star. Its orbit takes about 16 years to complete. On our timescale, that sounds manageable, but to complete that orbit, S2 must travel at speeds reaching over 3 million miles per hour. 3 million miles per hour? The entire width of the continental United States is about 2,800 miles. At 3 million miles per hour, a star would cross from the Pacific coast to the Atlantic in less than 4 thousandths of a second. One blink of an eye and it has crossed America more than 200 times. This is confirmed. Scientists tracked S2 for over 20 years using infrared telescopes. Its speed and orbital path provided the first ironclad proof that Sagittarius A star had to be as massive as calculated. The observation of S2 and other stars near the galactic center is considered one of the most important pieces of evidence in modern astronomy. A team led by 2 scientists, one German and one American, shared the Nobel Prize in Physics in 2020 for this work. Their decades of patience watching those stars curve around the invisible center gave humanity direct confirmation of what sits at the heart of our galaxy. Beyond raw speed, there is another strangeness near the galactic center. General relativity, Einstein's framework for understanding gravity and space-time, predicts that near extreme gravitational sources, time itself runs differently. Confirmed by atomic clock experiments on Earth and in orbit, gravity slows time. A clock at the surface of Earth ticks very slightly slower than a clock in orbit, where gravity is weaker. Near Sagittarius A star, where gravity dwarfs anything in our solar system by a factor of millions, this time difference becomes severe. A clock orbiting close to the black hole would tick dramatically slower than a clock here on Earth. From our perspective, watching something fall toward the event horizon of a black hole, it would appear to slow down and eventually freeze at the boundary, never crossing it. From the falling object's perspective, the crossing would happen rapidly. Time itself is not a fixed background. It bends. In the dense environment near the galactic core, stars also form differently. Gas and dust clouds are subjected to such powerful tidal forces that the process of star formation should, by standard physics, be disrupted. Yet astronomers have confirmed the existence of very young, massive stars orbiting close to the galactic center. Stars that by current models should not have been able to form there. Their existence is a confirmed mystery. Scientists have proposed they might have formed farther out and migrated inward, but this remains under investigation. The galactic center is the most extreme environment within our own galaxy, and from 26,000 light-years away, on a quiet rocky planet in the outer suburbs, we are watching it in real time. Stars accelerating to millions of miles per hour, time bending, young stars in places they should not exist, all of it visible from our backyard. And yet, our own galaxy's drama is about to be eclipsed by something on an even larger scale, because our galaxy is falling toward another one, and the one coming at us is even bigger. There is a galaxy visible to the naked eye from Earth's surface. On a dark, clear night, far from city lights, you can see it as a faint smudge in the constellation Andromeda. That smudge is the Andromeda Galaxy. It sits about 2.5 million light-years away. The light entering your eye right now left Andromeda 2.5 million years ago, when our ancestors were still early hominids, walking the African savanna and using stone tools. Andromeda is the largest galaxy in our local neighborhood. It is a spiral galaxy, similar in broad shape to the Milky Way, and it contains roughly 1 trillion stars. Our Milky Way holds between 200 and 400 billion. Andromeda is larger, older, more massive, and it is heading directly toward us. This is confirmed by decades of measurement. Andromeda is approaching the Milky Way at about 110 miles per second. That is fast enough to cover the entire distance from New York to Los Angeles in under 30 seconds. And it is coming at us across 2.5 million light years. Scientists have calculated the trajectory with high precision. In roughly 4 billion years, the two galaxies will begin their collision. The merger will play out over another 2 billion years after first contact. The entire process, from first interaction to final combined structure, will take about 6 billion years from now. Long after our sun has exhausted its fuel and expanded into a red giant, long after Earth as we know it no longer exists, the collision will still be underway. The collision will be spectacular by any measure. But here is the part that surprises most people. Almost no stars will actually collide with each other. The space between individual stars, even inside a dense galaxy, is so enormous that two galaxies passing through each other is largely an event of gravity, not impact. Stars will be flung into new orbits. Entire arms of both galaxies will be stretched, warped, and pulled apart. Gas clouds will collide and compress, triggering massive waves of new star formation. The night sky, had any observer existed, would be ablaze with newborn stars. After the collision, the two spiral structures will merge into a single elliptical galaxy. Scientists have even given it a name already, Milkomeda. The resulting galaxy will have no spiral arms, just a vast, rounded cloud of hundreds of billions of stars, settling into new orbits around a combined central structure. Our sun will survive the collision. It will be flung into a new orbit, likely much farther from the new galactic center than it currently sits, but it will survive. Earth, if it still exists by then, would look up at a night sky overwhelmed with stars, the merged galaxy blazing overhead in every direction. This is one of the most thoroughly modeled events in astronomy. Simulations run by scientists produce consistent results. The collision is coming, the physics is settled, only the fine details remain under refinement. 2 trillion stars combined. One merged galaxy. The largest event in our local cosmic neighborhood. But our neighborhood itself, the collection of galaxies we belong to, is a small cluster inside a much larger structure, and that structure is itself inside something larger still. The layers keep going, and each one dwarfs the last. Galaxies do not exist alone. They gather. Gravity pulls them together across millions of light years, assembling them into clusters and groups that drift through space as gravitational families. Our family is called the local group. It is a collection of about 80 galaxies spread across a region of space, roughly 10 million light years across. 10 million light years. That is the size of home on the next scale up. The local group has 2 dominant members, the Milky Way and Andromeda. Both are large spiral galaxies. The other roughly 78 members are smaller, many of them dwarf galaxies, some so faint they were only discovered recently. 2 dwarf galaxies orbit our own Milky Way. They are called the Large Magellanic Cloud and the Small Magellanic Cloud, and from the southern hemisphere they are visible as faint patches of light in the night sky. The Large Magellanic Cloud sits about 160,000 light years from Earth. It contains tens of billions of stars. From our position, it looks like a detached piece of the Milky Way drifting nearby. Gravitational models suggest the Milky Way is slowly pulling it in over vast timescales. Now, pull back from the local group entirely. View it from far above. The 10 million light-year diameter of the local group, with its dozens of galaxies and hundreds of billions of stars, looks like a small cluster of lights floating in darkness. Around it, on all sides, other galaxy clusters float in similar formations, some smaller than ours, some much larger. The nearest large cluster to us is the Virgo cluster, about 54 million light-years away. The Virgo cluster contains over 1,300 galaxies. Over 1,300 galaxies in a single cluster, many of them far larger than our Milky Way, all held together by gravity, all drifting in a gravitational dance that has been underway for billions of years. If the entire Milky Way were shrunk to the size of a grain of sand, the Virgo cluster would span a distance of roughly 3 miles. 3 miles of galaxy clusters, each grain of sand its own galaxy with hundreds of billions of stars. 3 miles of grains. Scientists have mapped the larger structure surrounding our local group. It includes the Virgo cluster and dozens of smaller clusters and groups, connected by thin threads of gas and dark matter. This larger assembly is called a supercluster, and ours has a name. It is called Laniakea, and it was only fully mapped in 2014. What that mapping revealed about the scale of our home address in the cosmos, and about a gravitational pull coming from a source we still cannot fully explain, is the kind of discovery that redraws every map you thought you had. For most of the 20th century, astronomers believed our galaxy belonged to something called the Virgo supercluster, a large grouping of galaxy clusters centered on the Virgo cluster, spanning roughly 110 million light-years. That was already a scale that required effort to comprehend. Then, in 2014, a team of scientists published a redrawing of the map. Using a new technique that tracked the motion of thousands of galaxies, measuring not just their positions but the direction of their gravitational drift, they identified the true boundary of the supercluster we live inside. The boundary was much larger than anyone expected. Our supercluster, now named Laniakea, a Hawaiian word meaning immeasurable heaven, spans roughly 520 million light-years from one side to the other. Inside it sit over 100,000 galaxies. Combined, they represent a mass equivalent to about 100 million billion times the mass of our Sun. 100,000 galaxies, each one a system of billions of stars, all of them gravitationally connected, slowly drifting, arranged in long filaments and sheets with enormous voids between them, all funneling toward a central region. Our local group, with its 80 galaxies and its 2 major spirals, sits near the outer edge of Laniakea. We are in the suburbs of a supercluster the way our solar system is in the suburbs of the Milky Way, far from the action, on the fringe. The action at the center of Laniakea is centered on the Virgo cluster and the surrounding region, but the gravitational story of this supercluster is defined by something else entirely. Something scientists can sense from how every galaxy in the structure is moving. Something pulling the entire supercluster in a single direction across space. A target. A source of gravity. Something massive enough to pull 100,000 galaxies. Scientists call it the Great Attractor, and it sits behind a wall of gas and dust within our own galaxy, making direct observation impossible with visible light telescopes. We can only infer its position and rough mass from the motion of everything around us. The Great Attractor pulls our entire Laniakea supercluster toward a region about 150 to 250 million light-years away. The entire 520 million light-year structure, with 100,000 galaxies inside it, is drifting in that direction. And behind the Great Attractor, farther still, lies an even more massive concentration of matter called the Shapley supercluster, which may be the true source of the pull. This is confirmed by galaxy velocity data. The motion is real. The pull is real. Its full source remains under investigation. Picture standing on a beach as the tide goes out. You feel the pull. You see the water moving, but you cannot see the moon from where you stand. You only know something large is pulling the water, and it sits beyond your view. That is humanity's current position in relation to the Great Attractor. We feel the pull. We know the direction. We cannot see the source clearly. And Laniakea itself, this immeasurable heaven containing us, is one of millions of similar superclusters spread across the observable universe. The next layer of scale is where the word enormous stops working entirely. For most of human history, the concept of a galaxy did not exist. For most of scientific history, scientists debated whether blurry patches of light in the sky were clouds of gas inside the Milky Way, or entirely separate systems at unimaginable distance. That debate was settled in the 1920s. Galaxies, as independent systems of billions of stars, became confirmed. It took another several decades to understand that galaxies cluster, then more decades to map superclusters. Each revelation required new technology, new methods, and the willingness to accept that the previous understanding of scale was too small. Laniakea followed the same pattern. The tool that unlocked it was called Cosmic Flows 2, a database of galaxy velocities compiled by an international team of scientists. Instead of simply charting where galaxies are located, the team charted where galaxies are flowing. Gravity shapes motion. If you map the direction every galaxy is drifting, you can trace the shape of the gravitational basin pulling them together. The way you could map a valley's shape by tracking which direction every stream inside it flows. When scientists applied this to thousands of galaxies across hundreds of millions of light years, the basin revealed itself. A single continuous gravitational structure, 520 million light years across, containing our local group at its edge and the Virgo cluster region near its gravitational heart. They named it Laniakea. The discovery was published in the journal Nature in September 2014. It redefined our cosmic address overnight. Before that paper, scientists placed us inside the Virgo supercluster, a structure about 110 million light years across. Laniakea is 5 times larger than that. Our real home address had been drastically underestimated. Here is the detail that carries weight. Even within Laniakea, with its 100,000 galaxies and its 520 million light-year span, the structure is mostly empty. The galaxies and clusters do not fill it uniformly. They trace along filaments, like cobwebs stretched across a dark room, with vast empty regions between them. The filled parts are thin threads. The empty parts are enormous bubbles. When scientists visualized Laniakea in 3 dimensions, what emerged looked like a glowing jellyfish. Trails of galaxies streaming inward, like tentacles toward the dense central region. Our local group sits at the far end of one of those tentacles. And here is the scale reckoning that Laniakea forces. Our entire Milky Way, with its 400 billion stars and its 100,000 light-year width, occupies a volume within Laniakea that represents roughly 1/5 billionth of the supercluster's total volume. 5 billion Milky Ways could fit inside Laniakea. That ratio is for the Milky Way, which already felt incomprehensibly large, 100,000 light-years across, and it represents 1/5 billionth of the structure we live inside. Now, Laniakea itself, this thing that dwarfs our galaxy by 5 billion to 1, is one supercluster among millions in the observable universe. The observable universe contains roughly 2 trillion galaxies, confirming that number required a fundamental revision of previous estimates, and the process that led to that revision produced one of the most startling corrections in the history of modern science. Scientists had been off by a factor of 20 for decades, and nobody knew. Every galaxy in our cosmic neighborhood is moving. Scientists confirm this by carefully measuring the velocities of thousands of galaxies across hundreds of millions of light years. The measurements revealed something that no one had cleanly articulated before. Everything in our region of the universe is drifting in the same direction. The Milky Way, Andromeda, our entire local group, the Virgo cluster, every galaxy within Laniakea, all of them streaming, slowly but relentlessly, toward a region of space that sits behind a wall of gas and dust in the plane of our own galaxy. That region is called the Great Attractor. The Great Attractor sits approximately 250 million light-years from Earth in the direction of the constellations Centaurus and Norma. Its total mass is estimated to be equivalent to tens of thousands of times the mass of the Milky Way. A concentration of matter so extreme that its gravitational fingerprint reaches across hundreds of millions of light-years and nudges everything in the vicinity. The challenge is that the Great Attractor sits almost exactly behind the densest part of our galaxy's dust and gas disk. When astronomers point optical telescopes in that direction, all they see is the Milky Way's interior. the view is blocked. Scientists use X-ray and radio telescopes, which can penetrate the dust, to peer through and identify the clusters and superclusters lurking behind the wall. What they have found is a concentration of galaxy clusters, the most prominent being a structure called the Norma cluster, a rich gathering of galaxies confirmed to lie at the heart of the Great Attractor region. But even the Norma cluster may not be massive enough to account for all the gravitational pull scientists measure. Behind the Great Attractor, farther still, sits the Shapley supercluster. At roughly 650 million light-years from Earth, the Shapley supercluster is one of the most massive concentrations of matter in the observable universe, containing dozens of galaxy clusters and tens of thousands of galaxies. Scientists believe the Shapley supercluster contributes significantly to the total gravitational pull our region experiences. So the picture that has emerged, through decades of confirmed measurements, is a chain of gravitational influence. The Shapley supercluster pulls on the Great Attractor region. The Great Attractor region pulls on Laniakea. Laniakea pulls the local group, and the local group carries our Milky Way along for the journey. An invisible chain, a gravitational current, and we are passengers on it, moving at hundreds of miles per second without feeling anything at all. There is an additional layer that scientists debate, still under investigation. Some researchers have proposed that an even larger structure exists beyond the Shapley supercluster, a concentration they call the dipole repeller, a region of space so empty that its lack of mass creates a kind of pressure, pushing our part of the universe in the same direction the Great Attractor pulls. Both a push and a pull, cooperating across distances of billions of light years. If confirmed fully, this means our region of the universe is caught between two enormous forces, one pulling us forward, one pushing us from behind, both operating across scales that make Laniakea look small. And Laniakea already contains 100,000 galaxies. The observable universe contains 2 trillion of them. That number was wrong for decades. When the correction arrived, it arrived suddenly, and it changed the count by a factor of 20. For most of the late 20th century, scientists estimated the observable universe contained roughly 200 billion galaxies. 200 billion was already an almost unreachable number, each galaxy holding hundreds of billions of stars. The math alone produced numbers that lost all connection to human experience. Then, in 2016, a team of scientists published a new analysis. They used data collected by the Hubble Space Telescope and combined it with sophisticated mathematical models to estimate how many galaxies existed in regions of the universe, too faint and too distant for any telescope to directly observe. Their conclusion revised the galaxy count upward by a factor of 20. 2 trillion galaxies, confirmed by peer-reviewed analysis published in the Astrophysical Journal. The previous estimate of 200 billion was based on the galaxies telescopes could directly detect. The new analysis accounted for galaxies that existed in the early universe and have since merged into larger structures. Galaxies too dim and too distant to be seen with current instruments. And galaxies in the vast regions of the universe that no telescope has yet pointed at. When all of that was folded in, the count multiplied 20 times over. 2 trillion is 2 million million. If every human being alive on Earth today spent their entire life counting galaxies at 1 per second, the combined count of every human who has ever lived across all of recorded history would still fall short. Now, apply the star count to 2 trillion galaxies. The average galaxy holds perhaps 100 billion stars. Multiply those 2 numbers together. The result is a figure so large it has no practical meaning in human terms. One estimate suggests the observable universe contains more stars than there are grains of sand on every beach and desert on Earth, combined, multiplied by roughly 10,000. And the observable universe is not the whole universe. The observable universe is defined by a specific boundary. The distance light has had time to travel since the universe began, about 13.8 billion years ago. Everything within roughly 46 billion light years in every direction falls within the observable sphere. That sphere contains 2 trillion galaxies. But the universe did not stop at the edge of what we can see. Space continued expanding beyond that boundary, carrying matter with it. Whatever sits beyond our observable horizon has been unreachable since the beginning of time. We cannot see it. We cannot signal it. We cannot know it directly. Scientists are confident the full universe extends far beyond the observable portion. How far is a question that sits at the boundary of confirmed knowledge and theoretical modeling? What sits beyond the horizon of our vision, the structures that exist in the unobservable universe, the galaxies and clusters and superclusters spread across distances we cannot measure directly, remains one of the greatest open questions in all of science. But even within the observable universe, the structures scientists have confirmed defy expectation. The cosmic web, the largest confirmed structure in existence, reveals that the 2 trillion galaxies are arranged into a pattern so vast and so specific that it looks, under the right visualization, like something that should not exist by accident. And one region of the observable universe sits almost completely empty. A void so large and so barren that its existence forced scientists to question whether the universe is as smooth and uniform as the standard model of cosmology predicted. That void has a name, and its size is deeply unsettling. Pull back far enough from any single galaxy, any cluster, any supercluster, and something remarkable appears. The universe is not a uniform fog of evenly distributed matter. It has shape, enormous, repeating, 3-dimensional shape. Scientists call it the cosmic web. Confirmed through decades of galaxy surveys and supported by computer simulations that match observed data with striking accuracy, the cosmic web describes the large-scale architecture of the entire observable universe. Matter, meaning galaxies, gas, and dark matter, arranges itself into long filaments, flat sheets, and dense nodes where filaments intersect. Between these structures sit vast, nearly empty regions called voids. The result looks, under the right visualization, like a 3-dimensional spiderweb stretched across billions of light years. The filaments are rivers of matter. Galaxies drift along them the way water beads along a thread. Where 2 or more filaments cross, gravity concentrates everything into dense nodes. Those nodes are the largest galaxy clusters in the observable universe, containing thousands of galaxies packed into relatively small regions of space. Here is the scale that restructures the imagination. A single filament of the cosmic web can stretch hundreds of millions of light years from end to end. The Milky Way, 100,000 light years wide, would be invisible on a map of a single filament. It would not even register as a dot. Scientists built the first large-scale map of the cosmic web in the 1990s using data from the first major galaxy surveys. What they saw shocked them. Structure at scales far larger than theory at the time predicted possible. The universe seemed too organized, too patterned, for a model based only on gravity working on a roughly uniform starting distribution. Dark matter became central to the explanation. Ordinary matter, the kind that makes up stars, planets, and everything you can touch, accounts for only about 5% of the universe's total mass and energy. Dark matter, which does not emit or absorb light, but does exert gravitational force, accounts for about 27%. The cosmic web is believed to be shaped first by dark matter filaments, with ordinary matter, and therefore galaxies, falling into those dark matter structures and lighting them up. The dark matter web forms first, invisible, enormous, spreading across the universe. Then galaxies assemble along it, tracing its outline in light. Computer simulations of this process, run on the most powerful supercomputers ever built, produce results that match the observed cosmic web with remarkable accuracy. The simulations start with the conditions of the very early universe and run forward 13.8 billion years. What emerges looks almost identical to what telescopes observe. This is considered one of the strongest confirmations of the dark matter model, and yet, Scientists confirm they still do not know what dark matter actually is. No direct detection has been made. Its existence is inferred entirely from its gravitational effects. The thing that built the largest structure in the observable universe remains unidentified. Every galaxy you have ever seen in a photograph, every cluster, every supercluster, every structure named in this journey so far, all of them sit along the filaments of this web. The voids between those filaments are where things get genuinely unsettling. Because one of those voids is large enough that standard cosmology, the accepted model of how the universe works, struggled to explain how it could exist at all. It is called the Botha's void, and standing at its edge, metaphorically speaking, is one of the more disorienting experiences science can offer. In 1981, a team of astronomers mapping the distribution of galaxies in a region of the sky called Botha's made a discovery that stopped the field cold. They found a hole, a spherical region of space approximately 330 million light-years across, containing almost nothing. No galaxy clusters, no filaments, no significant concentrations of matter. A near-perfect bubble of emptiness in a universe supposed to be filled with structure. They called it the Botha's void. To understand why this disturbed scientists, consider what the cosmic web predicts. Matter should distribute itself along filaments and nodes, yes, but the voids between them should be scattered and varied in size. The largest voids predicted by standard cosmology sit in the range of a few tens of millions of light-years across. The Botha's void is 330 million light-years across, an order of magnitude larger than models comfortably predicted. Here is the scale comparison that tends to produce silence. If the Milky Way sat at one edge of the Botha's void, and you wanted to walk to the other side, traveling at the speed of light the entire time, the journey would take 330 million years. Our galaxy is 100,000 light-years wide. The void is 3,300 times wider than our entire galaxy. 3,300 Milky Ways laid end to end would barely span it. Inside the Botha's void, a handful of galaxies exist. About 60 have been identified scattered through its interior. 60 galaxies across 330 million light-years. The surrounding universe has thousands of galaxies in regions a fraction of that size. The void is not perfectly empty, but it is extraordinarily, deeply underdense. One astronomer, upon reporting the discovery, noted that if the Milky Way sat at the center of the Botha's void, humans would not have known other galaxies existed until the 1960s. Our telescopes, for most of the 20th century, would have seen only darkness in every direction. The nearest neighboring galaxy would have sat beyond detection range. The entire edifice of extragalactic astronomy might have been delayed by decades because there would have been nothing nearby to find. Science has proposed several explanations. One theory suggests it formed through the merger of multiple smaller voids over billions of years. Another proposes subtle variations in the early universe's density seeded certain regions with less matter from the start, allowing them to empty out over time as surrounding gravity pulled material toward denser areas. Both remain under investigation. Neither fully resolves the discomfort the Botha's void creates for standard models. What confirmed science can say is this: the void is real, it is measured, and its size sits at the upper edge of what current models predict as possible, if not slightly beyond it. Whether it represents an extreme outlier or a hint at something the standard model of cosmology is missing remains an open question. The universe contains many such voids. Most are smaller than Botha's. A few candidates may be comparable, and at least one structure on the opposite end of the scale, a concentration of matter rather than an absence of it, is so enormous it raises a challenge of a different kind. Because the universe is supposed to look the same in every direction at the largest scales. Smooth, uniform, the same. And one structure in the sky violates that assumption so severely it should not exist under the rules of standard cosmology. Its name is long. Its implications are longer. The universe, at its largest scales, should be smooth. This is one of the foundational assumptions of standard cosmology, called the cosmological principle. Look in any direction across distances of hundreds of millions of light years, and the universe should appear roughly the same. Similar density, similar distribution of matter. No single region dramatically different from another. The Hercules Corona Borealis Great Wall disagrees. Identified in 2013 and later confirmed through additional analysis, this structure is a concentration of galaxy clusters so enormous it stretches an estimated 10 billion light years from end to end. Scientists identified it by mapping the positions of gamma-ray bursts, the brightest explosions in the universe, which trace the locations of massive galaxy concentrations across cosmic distances. 10 billion light years. The observable universe is about 93 billion light years across. The Hercules Corona Borealis Great Wall spans roughly 1/10 of the entire observable universe in a single direction. Standard cosmology sets a theoretical size limit for structures that gravity can build over the age of the universe. That limit sits at around 1.2 billion light years. The Hercules Corona Borealis Great Wall is approximately 8 times larger than that theoretical maximum. This is a confirmed detection with a caveat. The structure has been identified through statistical clustering of gamma-ray burst positions, and some scientists debate whether the clustering represents a true physical structure or a statistical artifact of the mapping technique. The debate is ongoing. The observations are confirmed. The interpretation remains under active scientific discussion. But if it is a true structure, it is a serious problem for the cosmological principle. A single continuous concentration of matter, 10 billion light years long, means the universe is dramatically unsmooth in at least one direction. It means the standard model of how the universe evolved from a nearly uniform state after the Big Bang may be missing something fundamental. The cosmological principle is not a law of nature. It is an assumption, supported by considerable evidence at smaller scales, but an assumption nonetheless. The universe does not owe us smoothness. Here is the implication that follows from this uncertainty. If the universe is unsmooth at scales of 10 billion light years, then maps of the cosmos built on the assumption of uniformity may be systematically incorrect in ways scientists have not yet fully characterized. The entire framework for measuring the universe's structure and evolution rests partly on that assumption. Cracks in it are worth attention. Astronomers continue to map the distribution of gamma-ray bursts and galaxy clusters to test whether the Great Wall holds up under greater scrutiny. The next generation of telescopes, already under construction in various forms, will produce data detailed enough to settle the question within the coming decades. For now, the Hercules Corona Borealis Great Wall sits at the edge of what science can confidently confirm, large enough to challenge the rules, measured enough to demand an explanation. And it exists inside an observable universe that began as something almost unimaginably different from what it is today. A universe that was once smaller than an atom, hotter than anything that exists now, and left behind a faint glow that still fills all of space. That glow is the oldest light in existence, and it carries information about the first moments of everything. Roughly 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons and form the first neutral atoms. Before that moment, the universe was a dense, opaque plasma, so hot and so compressed that light could not travel freely through it. Photons bounced endlessly off charged particles, going nowhere, trapped. When the first atoms formed, the universe became transparent for the first time. Light suddenly had room to move. The photons that had been trapped in the plasma released all at once and streamed outward in every direction. That light is still traveling. It fills the entire observable universe right now. You are surrounded by it at this moment. Scientists call it the cosmic microwave background. It was predicted theoretically and then discovered accidentally in 1965 by 2 radio astronomers who initially thought the faint signal contaminating their antenna was bird droppings. It was not. It was the oldest light in the universe, arriving from 13.4 billion years ago, mapped across the entire sky in every direction. When scientists measure the cosmic microwave background precisely, they find it is almost perfectly uniform. The temperature of this ancient light varies by only about 1 part in 100,000 across the entire sky. The universe, 380,000 years after its birth, was extraordinarily smooth. But those tiny variations matter enormously. The slightly denser spots in the early universe, where the temperature of the cosmic microwave background is fractionally warmer, represent the seeds of everything that came after. Gravity amplified those tiny density differences over billions of years. Dense spots attracted more matter attracted more matter still. Over time, those microscopic variations in the early universe grew into galaxy clusters, filaments, superclusters, and the entire cosmic web. Every galaxy that exists, every star, every planet, every living thing, grew from fluctuations smaller than 1/10,000% in the density of matter 13.8 billion years ago. Confirmed. Mapped in extraordinary detail by dedicated space missions. The cosmic microwave background also carries the most precise measurement of the universe's age, its composition, and its geometry. From the pattern of temperature variations alone, scientists determined the universe is 13.8 billion years old, flat in geometry to extraordinary precision, composed of 5% ordinary matter, 27% dark matter, and 68% dark energy. Dark energy is the most abundant component of the universe. Scientists confirm it exists. They confirmed it drives the accelerating expansion of the universe. They do not know what it is. This is confirmed unknown territory. The cosmic microwave background also contains faint imprints of gravitational waves from the earliest moments of the universe, ripples in space-time from the first fractions of a second after the Big Bang. Detecting these imprints cleanly would provide the first direct observational evidence of inflation, the period of extraordinarily rapid expansion in the universe's first moments. Right now, ancient photons from the edge of the observable universe are passing through you, through the room around you, through the entire Earth. The universe's oldest message, traveling since 380,000 years after everything began, still in transit, still carrying its information. And the universe that released those photons has been expanding ever since. Expanding in a way that makes the 2 trillion galaxies inside it progressively harder to reach. Some of them are already gone forever. Edwin Hubble confirmed it in 1929. Every galaxy beyond our local group is moving away from us. The farther away it sits, the faster it recedes. The universe is expanding. Space itself is stretching, carrying galaxies apart like dots drawn on an inflating balloon. This expansion has consequences that compound over distance in a way that eventually becomes permanent loss. The rate of expansion means that for every additional 3.2 million light-years of distance between us and another galaxy, that galaxy moves away from us about 45 miles per second, faster than the one slightly closer. This is called the Hubble constant, and its precise value has been one of the most intensely debated measurements in cosmology for decades. The confirmed range sits around 67 to 73 miles per second per megaparsec, with the exact value still under active investigation. What this means in practical terms, galaxies far enough away are receding from us faster than the speed of light. This does not violate any physics. Light speed is a local limit, a speed limit for objects moving through space. Space itself can expand at any rate, and at distances beyond a certain threshold, space expands fast enough that even light traveling toward us cannot close the gap. That threshold sits at roughly 14 billion light-years from Earth. Every galaxy beyond that distance, and the vast majority of the 2 trillion galaxies in the observable universe sit beyond it, is already receding faster than light can travel. Their light can still reach us currently because it was emitted when they were closer, and light already in transit can still make the journey. But any light those galaxies emit from this moment forward will never reach us. They are already sending messages we will never receive. And the expansion is accelerating. Scientists confirmed this in 1999, a discovery that earned its researchers the Nobel Prize in Physics in 2011. The universe is not just expanding, it is expanding faster over time, driven by dark energy, the unknown force permeating all of space. As time passes, more and more galaxies will cross the threshold of permanent unreachability. In roughly 100 billion years, if intelligent beings still exist somewhere, the observable universe available to them will be dramatically smaller than the one visible from Earth today. Every galaxy beyond our local group will have receded beyond the point of detection. The night sky will show only the merged remnant of the Milky Way and Andromeda, surrounded by darkness. Everything else, the 2 trillion galaxies, the cosmic web, the superclusters, all of it will have vanished beyond reach. Future civilizations, if they exist but lack our current records, will have no way to know the universe was once full of structure. The evidence will be gone. We live at a specific and remarkable moment in cosmic time, early enough that the universe is still full of structure, old enough that we have developed the tools to observe and understand it, a window that is closing on both ends. The observable universe right now stretches about 46 billion light years in every direction. That is what we can currently see. But the full universe extends beyond that boundary, likely by an extraordinary margin. And what sits beyond our horizon may be the most staggering idea in all of science. Every second, the boundary of permanent separation moves closer. Right now, roughly 97% of the galaxies in the observable universe are already moving away from us faster than light. Their light, emitted in the past when they were closer, still reaches us, giving the illusion of a universe full of structure. But that light is old. What those galaxies look like today, what they contain, what might exist within them at this moment, is information we cannot access. The universe hides its present from us behind the delay of light travel and the acceleration of expansion. And it gets more permanent than that. Scientists have calculated that only the galaxies currently within our local group, about 80 galaxies, will remain gravitationally bound to us over cosmic timescales. Everything else, every cluster, every supercluster, every structure visible in the deepest telescope images humans have ever captured, will eventually recede beyond the point of any possible contact. The Virgo cluster, with its more than 1,000 galaxies, is already receding. The Coma cluster, one of the largest nearby galaxy concentrations, is moving away. The great filaments of the cosmic web are pulling apart. The voids are growing larger. The universe's large-scale structure is dissolving into isolation, driven by dark energy, one expansion increment at a time. This is confirmed physics. The math is settled. The timeline is enormous, stretching over tens and hundreds of billions of years, but the direction is locked. Here is what that means for the concept of knowledge itself. Any observation we make of distant galaxies today is both a scientific treasure and a countdown. The universe is showing us its contents in real time, but it is also slowly withdrawing them. Each year, the light from ever slightly more distant galaxies becomes the last light we will ever receive from those sources. Each year, some galaxies tip past the permanent horizon. Scientists estimate the current observable universe contains information representing an enormous fraction of what will ever be observable from Earth. Future observers, billions of years from now, will inherit a fundamentally smaller scientific universe, not because science regressed, but because the cosmos itself contracted their view. There is a specific measurement here that carries unusual weight. The most distant object ever observed from Earth is a galaxy that existed when the universe was only about 300 million years old, less than 3% of its current age. Its light traveled for over 13 billion years to reach us. When that light left, our sun did not exist. Earth did not exist. The entire solar system had not yet formed, and yet that ancient light arrived here, was collected by telescopes, converted into data, and interpreted by minds that evolved on a rocky planet orbiting an average star in a quiet corner of a galaxy in a supercluster, drifting toward an unseen gravitational source. The universe delivered a message from before our existence, and we read it. That capacity for observation, across distances and timescales that dwarf our entire history, is something worth sitting with. But the observable universe, vast and extraordinary as it is, represents only the portion of the universe we can access. Beyond the 46 billion light-year horizon sits a larger cosmos that physics says almost certainly exists, and that theoretical models suggest may be incomprehensibly larger than what we can see. The size of that larger universe, if theory holds, is a number that language and mathematics both struggle to handle. The observable universe spans about 93 billion light-years from edge to edge. That measurement surprises people who encounter it for the first time, because the universe is only about 13.8 billion years old. If nothing moves faster than light, how can the observable universe be wider than the distance light could have traveled since the beginning? The answer is expansion. Space stretched while light was traveling through it. A galaxy 13 billion light-years away, when it emitted the light we now receive, has since been carried by expansion to a position roughly 46 billion light-years from us. The light made the journey, but the source moved during transit. So the observable universe, everything within reach of any signal traveling at light speed since the Big Bang, forms a sphere roughly 46 billion light-years in radius in every direction, 93 billion light-years across. Inside that sphere sit 2 trillion galaxies arranged in the cosmic web, separated by voids, connected by filaments, all drifting according to the laws confirmed by observation. That observable sphere is a horizon, a boundary defined by time and the speed of light. Beyond it, the universe continues. Space did not end at the edge of what we can see. The Big Bang happened everywhere simultaneously, an expansion of space itself rather than an explosion into existing space. Every region of the universe shares the same origin moment. The laws of physics operate everywhere. Beyond our observable horizon, matter almost certainly exists in distributions similar to what we see inside it. More galaxies, more clusters, more superclusters, more cosmic web, more voids, continuing outward in every direction without a known edge. How far it extends is unknown. The universe may be infinite. It may be finite with a geometry that curves back on itself, though current measurements suggest it is flat to extraordinary precision. Flat geometry, confirmed by measurements of the cosmic microwave background, does not guarantee infinity, but it is consistent with it. Theoretical physics has something to say about the minimum size of the full universe, and the answer makes the observable universe look microscopic. The theory of cosmic inflation, the leading scientific framework for understanding the very first moments after the Big Bang, describes a period of extraordinarily rapid expansion in the first tiny fraction of the first second of the universe's existence. During inflation, space expanded at a rate far exceeding the speed of light, driven by a quantum field in a high-energy state. If inflation happened, and the evidence supporting it is strong, though not yet fully confirmed through direct observation, then the full universe is dramatically larger than the observable portion. How much larger depends on how long inflation lasted and how rapidly it proceeded. Conservative estimates place the full universe at roughly 100 times larger than the observable portion in every direction, making it about 10,000 times larger in volume. Moderate estimates push that figure to millions or billions of times larger. Extreme theoretical estimates, which we will examine shortly, produce numbers that have no analogue in human experience. The confirmed observable universe, 93 billion light-years of structured cosmos containing 2 trillion galaxies, may be a rounding error compared to the whole. And if certain theoretical frameworks are correct, What lies beyond our horizon is stranger than more of the same. It may contain regions where the physics we rely on simply does not apply. Cosmic inflation does not produce a gentle extension of space. Under the mathematics of inflationary theory, the process generates an almost absurd excess of universe beyond any observable boundary. Here is the theoretical framework, which scientists regard as strongly supported, but not yet fully confirmed through direct observational evidence. In the first tiny fraction of the first second after the Big Bang, a field of energy drove space to expand at an extraordinary rate. Every unit of space doubled in size, then doubled again, in rapid succession. The number of doublings, even over an inconceivably short time, accumulates into a final volume of space that dwarfs the starting point by an almost incomprehensible factor. The observable universe we can see represents the region of space that was roughly one atom in size just before inflation began. Inflation expanded that atom-sized region into the enormous sphere we now inhabit. But inflation did not expand just that atom. It expanded all the space surrounding it equally in every direction, with no boundary and no edge. The result is a full universe that, under moderate inflationary models, is at minimum roughly 10 to the power of 23 times larger than the observable universe in each direction. 10 to the 23. That is a 1 followed by 23 zeros. In terms of volume, the full universe would be 10 to the 69 times larger than the observable portion. More extreme models produce larger numbers still. Some theoretical frameworks generate a full universe so large that its size can only be written as 10 to the power of 10 to the power of 10, a tower of exponents that refers to a number with more digits than there are atoms in the observable universe. This is theoretical physics operating at its most extreme edge. The numbers are generated by equations that are well tested at smaller scales, but the specific predictions about the size of the full universe remain beyond any direct confirmation. Scientists take them seriously because the underlying mathematics is consistent. They hold them with appropriate uncertainty because the claim cannot yet be tested. What these numbers mean for the content of the universe is where things become genuinely strange. If the full universe is sufficiently large, and inflationary models suggest it almost certainly is, then every possible arrangement of matter that quantum mechanics permits must eventually repeat. The number of unique configurations of particles within any given volume is finite. If space is large enough, every configuration appears somewhere, including, by straightforward probability, a region of space identical to our observable universe, a region containing a galaxy identical to the Milky Way, a star identical to the Sun, a planet identical to Earth, and on that planet, by the same reasoning, a situation identical to this one. This is a confirmed implication of the mathematics, assuming the universe is sufficiently large. Whether the universe is sufficiently large remains unconfirmed, but if inflation proceeded as the models suggest, the full universe is large enough. And in a universe that large, identical copies of every possible configuration exist, separated by distances so enormous they can never interact, never observe each other, never communicate. This is not the multiverse in the science fiction sense. It is a direct consequence of quantum mechanics and inflation, applied to a very large, possibly infinite space. And it is not even the strangest version of the multiverse that physics produces. Scale analogies break down at this level of comparison, but attempting them reveals something important about the relationship between what we can see and what likely exists. Start with the observable universe, 93 billion light-years across, containing 2 trillion galaxies, the cosmic web, the superclusters, the filaments, the voids, everything confirmed by observation. Shrink all of that to the size of Earth, a sphere roughly 8,000 miles in diameter. On that scale, the full universe, under moderate inflationary models, would extend so far in every direction that the observable universe sitting at its center would be smaller than the smallest particle any instrument has ever detected. The full universe on this scale would be larger than the observable universe at its actual size. You would need the full universe to be its actual size just to contain a representation of the full universe at a scale where the observable universe fits inside Earth. The analogy collapses not because the comparison is wrong, but because the numbers involved operate beyond the reach of spatial intuition. Human brains evolved to navigate distances from inches to miles. The brain has no sensory experience of light years, no embodied reference for billions of light years, and absolutely no internal representation of numbers like 10 to the power of 10 to the power of 10. This is an important point to hold carefully. When cosmologists talk about the size of the full universe, they are working with mathematics that they trust because it produces correct predictions in the regimes where it can be tested. But they are applying it to a domain where no test is possible. The honest position is that the full universe is almost certainly enormously larger than what we observe. The precise figure carries genuine uncertainty, and the uncertainty itself is difficult to bound. What the scale exercise reveals, even without exact numbers, is that the observable universe is almost certainly a local sample of a vastly larger whole. The 2 trillion galaxies, the cosmic web, the entirety of what telescopes have ever imaged, is a small region of space, a neighborhood, a patch, and neighborhoods differ from the broader city around them. If the full universe is large enough, and theory strongly suggests it is, different regions of it will have different histories, different densities, different concentrations of matter. Some regions will have formed more stars, some will be darker, emptier, colder. Some will be closer to the end of their stellar lifetimes. But standard inflationary theory predicts something more radical than simply more of the same. It predicts that inflation may still be happening right now in regions of space beyond our horizon. That inflation never stopped everywhere simultaneously, but continued in some regions while ending in others. Each region where inflation ends becomes a separate expanding universe, a bubble of space with its own physics, its own constants, its own history. This is called eternal inflation, and it produces a multiverse of a specific kind, not parallel dimensions, but physically real regions of space, entirely beyond our reach, each evolving under its own conditions. Some of those regions may have different values for the constants of physics, different strengths of gravity, different masses for electrons, different rates of nuclear reactions, and in many of those regions, stars cannot form, life cannot exist. Nothing we recognize as structure or complexity is possible. We happen to live in a region where the constants permit complexity. Whether that is chance, selection, or something else, remains one of the deepest unresolved questions in science. Every measurement ever made confirms the same values for the fundamental constants of physics. The strength of gravity, the charge of the electron, the speed of light, the force binding atomic nuclei together. These constants appear identical everywhere humans have been able to observe, across the entire observable universe and back to within fractions of a second of the Big Bang. But constants confirmed within the observable universe are not necessarily universal in the mathematical sense. They may be local values, properties of the specific region of space that inflation carved out to become our observable universe. This is a theoretical prediction, not confirmed observation. Scientists take it seriously because it follows from inflationary models that have strong observational support in other respects. The claim is under active investigation. The idea goes like this. During inflation, the energy field driving expansion settled into a specific low-energy state, as inflation ended in our region of space. That settling, called a phase transition, determined the values of the physical constants in our bubble of universe. A slightly different settling elsewhere would produce different constants. And the settling is, at the quantum level, random. Different constants produce dramatically different universes. Increase the strength of gravity slightly, and stars collapse before nuclear fusion ignites. Decrease the strength of the force holding atomic nuclei together slightly, and atoms heavier than hydrogen cannot form. Change the ratio of matter to antimatter in the early universe, and everything annihilates, leaving nothing behind. The range of constant values that permit the existence of atoms, stars, planets, and chemistry is narrow. Many physicists have calculated this range with considerable precision. The universe sits inside that narrow window. Whether it sits there by chance, by some unknown physical necessity, or because only observers in life-permitting regions can ask the question, is one of the most debated topics in theoretical physics. Astronomers have searched the observable universe for any variation in constants across cosmic distance and time. Some studies have reported subtle hints of variation in the fine structure constant, a number governing how light and matter interact across different directions in the sky. These results are preliminary and contested. Most measurements confirm uniformity to high precision. If constants are truly uniform across the observable universe, it may mean our observable patch is simply too small to show variation, the differences lying beyond the horizon in regions with genuinely different physics. Or it may mean constants truly do not vary, placing limits on certain versions of eternal inflation. Here is the implication that produces the deepest pause. If other regions of the full universe have different physical constants, they are not just different places, they are different kinds of places. Places where the structures we depend on for everything, atoms, molecules, stars, gravity, electromagnetic forces, do not exist in any recognizable form. A universe where chemistry cannot happen is a universe where information cannot be stored in the complex ways life requires. Those other regions are not just uninhabited. They may be uninhabitable in ways that require no inhabitant to confirm. And in the extreme version of this picture, our universe, with its 2 trillion galaxies and its billions of years of stellar evolution and its narrow constants, is one outcome in an eternal, ongoing process that generates every possible outcome simultaneously, forever. That process has a name, and one of its implications is among the strangest confirmed logical consequences in all of science. The multiverse is not a single theory, it is a family of theoretical frameworks, each arising from different areas of physics, each predicting something beyond the observable universe, each currently beyond direct confirmation. The version arising from eternal inflation predicts physically real regions of space, each an expanding bubble universe, each potentially with different physical constants, separated by inflating space that can never be crossed. Confirmed mathematical consequence of well-supported inflationary models. Observational confirmation, currently impossible. The version arising from a quantum mechanics is different. Every quantum event, the decay of a radioactive atom, the path a photon takes through a double slit, the energy level an electron occupies, exists in superposition until measured. The Copenhagen interpretation of a quantum mechanics says, superposition collapses to one outcome at measurement. A competing interpretation, called the many worlds interpretation, says superposition does not collapse. Every outcome occurs. The universe branches into copies, one for each outcome, with each copy unaware of the others. This is a legitimate scientific interpretation of quantum mechanics, not fringe speculation. It was proposed by physicist Hugh Everett III in 1957 and has been developed and defended by serious physicists ever since. Experiments cannot distinguish between the Copenhagen and many worlds interpretations because both predict identical observable results. The difference is entirely in the metaphysics, what the equations describe rather than what they predict for measurement outcomes. If the many worlds interpretation is correct, every quantum event throughout the history of the universe generated branching. The number of branches is effectively uncountable. Each branch is a complete universe, identical to ours up to the point of branching, diverging in every way afterward. In some branches, particular quantum events that happened here did not happen there, and history unfolded differently from that point forward. A third version arises from string theory and the landscape of possible vacuum states. String theory, a theoretical framework attempting to unify all forces of physics, predicts an enormous number of possible ways the extra dimensions it requires can be compacted. each producing different physical constants in the resulting four-dimensional universe. The number of possible configurations is estimated at 10 to the power of 500. A number so large it effectively means every possible set of constants is realized somewhere. Whether any version of the multiverse is real remains unconfirmed. Physicists continue to debate whether multiverse theories are scientific in the strict sense, meaning testable, or whether they represent a metaphysical extension of physics beyond the domain where science can adjudicate. What is clear is that several of the most successful physical theories that make precise, confirmed predictions about observable phenomena, naturally generate something beyond the observable universe when extended to their logical conclusions. The question of whether that something is real or whether the theories are simply incomplete is among the most important open questions in all of science, and one confirmed implication of a sufficiently large universe, whether multiverse or simply a very large single universe, involves probability in a way that most people find immediately unsettling. The argument is straightforward. The number of possible configurations of matter within any finite volume of space is finite, though extraordinarily large. Quantum mechanics places a fundamental limit on how finely matter and energy can be arranged. The number of possible arrangements of particles in a region the size of the observable universe, while astronomical, is a specific finite number. Physicists have estimated this number. It is approximately 10 to the power of 10 to the power of 118. A tower of exponents. A number with more digits than there are atoms in the observable universe. Enormous beyond any normal adjective, but finite. If the full universe is sufficiently large, specifically if it extends farther in space than the distance required for every finite configuration to repeat, then by pure probability, every possible arrangement of particles within an observable universe-sized volume must appear somewhere. Every arrangement. Including ones identical to our own observable universe. Including ones nearly identical, but with minor differences. The distance to the nearest identical copy of our observable universe, under this calculation, is estimated at roughly 10 to the power of 10 to the power of 118 meters. A number impossible to visualize or compare to anything meaningful, but a finite distance. Somewhere in a universe that extends far enough, that configuration exists, including necessarily a copy of Earth, a copy of every city on Earth, and a copy of every person on Earth in every arrangement that quantum mechanics permits, including the arrangement you are in at this exact moment. This is not speculation or science fiction. It is a direct mathematical consequence of quantum mechanics applied to a universe large enough for all configurations to repeat. The claim has been made explicitly by cosmologists, including the physicist Max Tegmark, who published it in peer-reviewed journals and developed it into a formal framework called the mathematical universe hypothesis. The confirmed part: quantum mechanics places a finite limit on possible configurations within any finite volume. Confirmed by the physics of the Planck scale. The unconfirmed part: whether the universe is large enough for repetition to occur. This follows from inflationary models that are strongly supported, but not proven beyond doubt. If the universe is infinite, repetition is guaranteed, not just probable. An infinite universe with finite possible configurations per unit volume must repeat every configuration infinitely many times. Here is what that means held plainly. Your specific arrangement of atoms, your memories, your current position and state either exists somewhere else in the full universe or in an infinite universe exists infinitely many times elsewhere. Each copy has no awareness of the others. Each copy experiences itself as the only one. Each copy is, from its own perspective, entirely real. Whether this should change how you think about identity, uniqueness, or the meaning of individual experience is a question philosophy has not settled. Physics offers the calculation. The interpretation is yours to carry, and the universe that contains all of this, all these scales, all these structures, all these possible configurations, will not last forever. Its end is confirmed. Its timeline is immense. And compared to how long the universe will exist after all the stars go dark, the age we currently live in is the briefest possible opening chapter. Every image ever taken through a telescope is a photograph of the past. This is not a metaphor. It is physics. Light travels at a fixed speed. The time it takes to cross any distance is real time, elapsed and gone. When astronomers point a telescope at a nearby star 4 light years away, they see that star as it was 4 years ago. When they image a galaxy 50 million light years distant, they see it as it was 50 million years ago. When the Hubble and James Webb Space Telescopes image galaxies near the edge of the observable universe, they are photographing events that happened over 13 billion years ago. The universe we observe is a layered historical document. Close objects appear recent, distant objects appear ancient. The deeper the telescope reaches, the further back in time the image represents. A photograph of the full night sky at every wavelength would be a time machine, showing different epochs simultaneously, all visible at once from a single location. This has been confirmed and exploited deliberately by astronomy. Scientists studying the evolution of galaxies compare nearby galaxies, showing their current form, with distant galaxies, showing their ancient form. The comparison reveals how galaxies change over billions of years, without requiring billions of years of observation. Distance provides the time axis for free. The most distant confirmed galaxy observations show objects from when the universe was only a few 100 million years old. Those early galaxies look dramatically different from modern ones. Smaller, more irregular, less structured. The cosmic web had barely begun to form. The first stars were only recently ignited. James Webb Space Telescope observations, ongoing since 2022, have pushed this record further and found something unexpected. Some early galaxies appear larger and more structured than current models predicted they should be at that age. Scientists are actively investigating whether this represents gaps in the standard model of galaxy formation, or whether some early galaxies formed stars and grew faster than expected. This remains under active scientific investigation, and it is genuinely exciting. The early universe is not behaving quite as cleanly as the models predicted. Here is the implication that carries the most weight. There is no such thing as seeing the universe as it is right now. Every observation is historical. Even the sun, 8 light minutes away, shows us a past state. The nearest large galaxy cluster is 54 million light years away, meaning we see it as it was 54 million years ago, before the first primates evolved on Earth. We have no idea what it looks like today. We will not receive that information for 54 million years. The universe as it currently exists, at this precise moment, is completely unknown to us. We see only its past. The deeper we look, the older the image. The edge of the observable universe shows us an epoch before stars, before galaxies, before any structure existed. The beginning. And on the other end of time, past the present moment we cannot directly observe, the universe continues its evolution toward an end that physics has mapped in considerable detail. That end is not a sudden event. It is a slow, cold, extraordinarily long unwinding that makes the current age of the universe feel like the first breath of a journey measured in incomprehensible eons. The universe is 13.8 billion years old. That is a long time by any human standard. Civilizations rise and fall in centuries. Species evolve over millions of years. The Earth itself is 4.5 billion years old. But the timeline of the universe's future death is so long that 13.8 billion years of existence registers as the opening moments of an almost infinitely longer story. The current era, scientists call it the stelliferous era, the age of stars, will last for roughly 100 trillion years. 100 trillion. The universe, at its current age of 13.8 billion years, is less than 1% through this first era. Stars are still forming across the cosmos. New solar systems are still assembling. The universe is, by its own standards, young. Around 100 trillion years from now, the last stars will exhaust their fuel. The smallest red dwarf stars, far more frugal with their hydrogen than our sun, will be the final ones burning. When they go dark, the universe enters its next era, the degenerate era. The remaining objects will be white dwarfs, neutron stars, and black holes. Cold, dense remnants of stars that lived and died. No new light, no new warmth. The temperature of the universe will approach absolute zero. The degenerate era lasts an almost unthinkable length of time. White dwarfs cool and fade over timescales extending to roughly 10 to the power of 37 years. That number is a 1 followed by 37 zeros. The entire current age of the universe fits into the first 13.8 billion years of this era. The era itself lasts so long that the current age of the universe is invisible on its timeline. After white dwarfs fade, quantum effects called proton decay, if protons are unstable, as some theories predict, may dissolve the remaining matter into radiation over timescales of 10 to the power of 40 years. If protons are stable, matter persists even longer, though subject to other quantum tunneling processes. Then comes the black hole era. Only black holes remain, slowly evaporating. Physicist Stephen Hawking predicted that black holes emit a faint trickle of radiation through quantum effects at their event horizons, gradually losing mass over vast timescales. This is called Hawking radiation and is theoretically confirmed, though too faint to have been directly observed yet. The largest black holes, supermassive ones like Sagittarius A star, take roughly 10 to the power of 100 years to evaporate completely. When the last black hole evaporates, the universe enters what physicists call the dark era. All that remains is a cold, diffuse gas of photons and particles, spreading through an ever-expanding space, approaching the lowest possible energy state. This state is called heat death, maximum entropy, the end of usable energy. No gradients left to drive any process, no possibility of complexity, no information processing of any kind. The universe does not end in a dramatic event. It ends by becoming as close to nothing as something can be while still technically existing. And within all of that enormous timeline, humans arrived at the most luminous, most structured, most energetic era the universe will ever know. We exist at the peak. The cosmic timeline has a shape, a long rise, a luminous peak, and an unimaginably long decline into cold and silence. We are at the peak. The stelliferous era, the age of stars, represents the most energetic, most structured, most information-rich period the universe will ever experience. Hundreds of billions of galaxies blazing simultaneously. Trillions of stars fusing hydrogen into heavier elements and radiating energy into space. Complex chemistry forming on rocky planets, orbiting stable stars. The conditions for biology, for thought, for awareness exist only in this era. After this era ends, no new stars will form. The raw material for stellar ignition will be locked inside cooling remnants. The universe will never again have the energy density, the chemical complexity, or the thermal gradients necessary for life as we understand it. The window for biology is open right now, during the first 1% of the stelliferous era, and it will close when the last stars die. Humans, and all life on Earth, exist at the cosmically privileged moment, early enough that the universe is still warm and bright, old enough that enough stellar generations have lived and died to scatter the heavy elements, carbon, oxygen, iron, calcium, into the interstellar medium, elements that assembled into planets and into our bodies. We are made of atoms forged inside stars that died before the sun was born. Ancient stellar furnaces ran their reactions, ended in supernova explosions, scattered their contents across the galaxy, and that scattered material eventually collapsed into the solar system, into Earth, into us, confirmed by the isotopic signatures of elements in our bodies and in meteorites. And we are the only known witnesses to all of this. No other species on Earth has developed the tools, the mathematics, the instrumentation, or the framework to understand what the universe is or how large it is. No other planet, as far as confirmed science can determine, currently hosts a civilization capable of this awareness. The search for signals from other civilizations has found nothing confirmed in decades of listening. This may mean other civilizations are rare. It may mean they exist, but communicate in ways we are not yet detecting. The answer remains unknown. What is confirmed? At this specific moment in cosmic history, on this specific planet orbiting this specific star, in the outer arm of this specific galaxy, there exist beings who have measured the observable universe to 93 billion light years, counted 2 trillion galaxies, traced the cosmic microwave background to 380,000 years after the Big Bang, imaged the supermassive black hole at the center of their own galaxy, and worked out the likely end of the universe from first principles. The universe has been doing all of this for 13.8 billion years without awareness. Stars burning, galaxies colliding, voids expanding, the cosmic web assembling, all of it unwitnessed. Then, on a pale blue dot in an unremarkable location, something looked up and started measuring. Whether that is meaningful in any deep sense is not a question science can answer, but it is a fact. And facts at this scale tend to produce something that no other scale produces quite as cleanly. The final question waiting at the end of all this measurement is the one that started the entire project. The one that every scale we have crossed leads back to. The one sitting quietly underneath everything. What does it mean? Stand at the beginning of this journey. Earth, a basketball-sized rock orbiting an average star, one of 400 billion in a galaxy 100,000 light years wide. One of 2 trillion galaxies in the observable universe. The observable universe possibly a rounding error compared to the full extent of space. The full universe possibly one of infinitely many, all of it building toward a heat death so far in the future that the entire current age of everything is a fraction of the opening act. That is the picture science has assembled. Each piece confirmed to the precision available. Each edge of the picture marked clearly where confirmation gives way to strong theory, and where strong theory shades into active investigation. What does a human life mean inside this picture? The honest answer is that science does not address meaning. Physics describes structure, scale, process, and evolution. It does not assign significance. The universe does not perform indifference or care. It simply operates according to laws that happen to permit complexity, chemistry, biology, and the kind of neural architecture that asks questions like this one. But something happens when people genuinely absorb the scale. Astronauts described it from orbit. Scientists describe it when they process the implications of their own measurements. Philosophers have circled it for centuries. Something shifts. One response is smallness. If the observable universe contains 2 trillion galaxies, and the full universe contains infinitely more, and human civilization has existed for less than an eye blink of the stelliferous era, then human concerns seem to shrink past relevance. Wars over territory on a pale blue dot. Competitions for status among a few billion members of a single species on one planet. The grief and joy and ambition and fear of individual human lives, reduced by scale to something that barely registers. This response is understandable. It is also arguably missing something important. Consider the alternative framing. The universe produced the conditions for awareness on at least one world, possibly others, though none confirmed. On this one world, over billions of years of stellar evolution, chemical complexity, biological evolution, and cultural accumulation, something emerged that can look back at the process and understand it. That can measure the edge of the observable universe with instruments built from elements forged in ancient stars. That can work out the timeline of the universe's death from mathematics developed across a few centuries of human thought. The universe spent 13.8 billion years building the conditions for that, and the window for it is cosmically narrow. Physicist Carl Sagan put it plainly. We are a way for the cosmos to know itself. Science has not disproved that framing. And the scale, rather than making individual experience meaningless, can be read the other way. The rarity of complexity, the narrowness of the window for life, the specific series of stellar deaths that scattered the atoms in your body, the particular sequence of events on one pale dot that produced minds capable of understanding 13.8 billion years of history. All of it converging here, all of it producing the awareness necessary to ask the question. That is not small. That is extraordinary. What the scale of the universe does, if you let it, is recalibrate. The concerns that once felt enormous, the disappointments and the frictions and the ordinary grievances of a human life, retain their weight. They are real, but they sit inside something larger. They sit inside a universe that produced them, that permitted them, that in 13.8 billion years of operation arrived at this moment where they exist at all. The universe will not remember any of it. The heat death will erase every record, every galaxy, every star, every thought, every measurement taken on this pale dot, gone. But it happened. Confirmed. Measured. Witnessed. And for a brief moment in the first 1% of the age of stars, something looked up and understood.